Okay, maybe we can start. So, the way I see the last few classes we've been doing is basically as learning about ingredients to put together to create algorithms. Okay, and in that sense, we spent considerable amount of time talking about what we called empirical risk minimization. Okay, which is just the minimization. I wrote it for the gazillion time today. Just the minimization. The name stems from the fact that it comes from the minimization of the empirical risk for a given loss function. Okay, and then from this basic idea, we started exploring the few directions. Okay, the first thing we did was let's add. Well, I guess maybe if we want to really do an history of what we've been doing so far, we could say we started from linear models, least squares. Then we discussed what if we had a squared norm and we consider penalized empirical risk minimization. We then went on and consider different loss functions. Okay, and then every time we did Theorem, we realized that Theorem is not an algorithm, strictly speaking, because it replaces a problem that we cannot solve, the minimization of the expected risk. With a problem we can solve, but if, say, an optimization person comes in the room, this is not a solution, is a problem itself. And in fact, roughly speaking, half of machine learning is devoted to proving that this is fine, okay? And the other half is proving that you can solve this with some kind of gradient technique, okay? This distinction was blurred in the last couple of classes when we start to look at essentially computational tricks, optimization one, projection the other, and so how themselves can be seen as a form of modeling, okay? And we introduced 2 classes ago the idea of implicit regularization, aka iterative regularization. The motto here was optimization regularizes. What this means is that an optimization algorithm, and we discussed in detail a simple case, which is gradient descent for least squares, not only converges, but one, it converges to specific solution, say minimal norm solution. So in that sense, it has a bias, which is implicit because it doesn't appear as a constraint, but is hidden in the way the iterative procedure explores the space. And 2, in the path of solution that is created, along the iterations, we somewhat explore solution in a similar way as you do when you change lambda. Okay, so in that sense, the term regularization here has a precise meaning. And if you want, is what we call learning by projection. Where if you want here, we can say that dimensionality reduction regularizes in a way. Okay, the idea that you squeeze the data in a smaller format, either with deterministic techniques like PCA or randomized techniques like sketching, linear or nonlinear, is a way to in fact enforce models in your data. Okay, and while here statistical and computational aspects are completely divided, here they somewhat get more blurred. Okay. The one thing that we have not, we used always least squares and linear models as the proof of of our starting point. The reason is because they're simple, okay, and because we can really get self-contained, quite satisfactory self-contained expositions of these ideas. Okay. Turns out that when you move to other, what we discussed a bit is moving to different loss functions. Okay, and already that one is not so the map of things that we know and we can prove. The thing that they work, we know, but the fact that we prove that they work is not always true. We move to different optimization algorithm. We discuss gradient descent, subgradient descent, stochastic gradient descent, and we mentioned tricks like mini batching and acceleration. There are two things that we haven't done pretty much at all. We discussed nonlinear models, but only linearly parameterized linear model. Sometimes we went all the way down, sometimes we just hinted at it, but we basically discovered that once you know how to handle this and you're dealing with these norms, if instead of this model you use a feature map or a kernel, pretty much the same reasoning apply, okay? We have not ever changed this norm, and we have not changed this form beyond the linearly parameterized model. So in the next couple of classes, that's what we're going to do. What we do today is that we replace this with something else, with some other form of regularizer, okay? And we try to make sense of how this new form of regularizers compare to what we've been doing so far, both from a computational point of view and a modeling point of view. And the keyword for today is sparsity. So we begin just warming up, saying what does it mean to be, what it means for a model to be sparse, okay, in words, why would you care, and how do you actually formalize this idea, okay? In words, you can say that the solution depends on few building blocks. This is vague enough, okay? What are the building blocks? You're going to be clear in a minute. But in some sense, the idea is that you have several building blocks, but your solution doesn't depend on them all, okay? And already at this level of generality, you can ask, why would you care, okay, for something like this? And we can make a long list, but you know, the one that I mentioned, that we mentioned in the notes are essentially three, in the order that I like best. This list of symbols is my way to write interpretability, okay? What does it mean? If you have something that depends on not a lot of things, but only a few, and you know what they are, you can go and look at them and say, what are they, okay? What do they mean? So if you have a model where you try to understand not just if there is my face or not in a picture, but you know, if I'm going to be more at risk of a certain kind of disease, and you have measurements of, I don't know, different kind of, so gene expression or physiological measurements, then you can go in and check, okay? And before you go on, the doctor can just decide if you're going to do extra tests or try to understand better if what you're saying with your statistical model confirm what's known about that, you know, say, disease in this case that you're studying, okay? There are many, I would say, whenever machine learning departs a bit from just AI-ish application and go more towards data science-ish application, the second thing is often more important than just brute force good prediction, okay? You want to use machine learning as a lens to look at complicated high-dimensional data and make sense of them. And by no means each view is final. It's just a view. You know, you can view them with this machine learning instruments, with this machine learning instrument. And interpretability really become a prominent requirement oftentimes. To me, this is really one of the main and most important reasons why this kind of ideas became fashionable and important in machine learning. But there are many others. One is high-dimensional statistics and probability. Synthesized in the n much smaller than P or D motto, you have many more parameters than observations, okay? And long story short, this is actually what I've been discussing for the last 3 weeks. It's just that we'll just find out yet another way of doing it, okay? And finally, the obvious thing is that you're compressing. If your model can be expressed in somewhat compact form, you have compression, and this can be useful for computational purposes or when you have to apply your model and so on and so forth. Okay. All right. So this is just a little bit of a story, but again, what do we mean by building blocks? This is my dyslexic Italian English. How do you formalize this idea? And it turns out that you again go back to linear models. Okay, why? Because that's what we know how to do. And we say that if you have a function W transpose X, you can write it as a combination of the entries of the vector. Okay, so X is just going to be X1, XD. And sparse means that many entries of this vector are not important. Okay, so there are Wj equal to 0. Okay, for some of the j between 1 and d. So if the sentence hidden here, if this sentence is very vague, this is actually extremely precise. You have a linear model, and then you have that sum of the vectors, some of the coefficients on the entries are 0. Okay? Notice that once you write that down, you can attach. I don't know if you discussed this. I don't remember if we did it first class. But you can view these. You can attach a story to this equation, right? You can view these as measurements, okay? And this is as the importance of a measurement. So if this is 0, that measurement doesn't matter at all. If this is big, this intuitively the measurement matters much more. So this is the interpretability story. I do these linear measurements, I combine them, they each vote to decide whether this is a much positive, what is the value of f, and if somebody has a strong vote, it counts more than somebody else. But here the whole point is that this is kind of what we're doing so far, but really here we want to know who doesn't count at all. Okay, we want to throw them out. So the question is, if we accept this, the question is how do we incorporate this assumption in a learning algorithm, and what kind of computation we're going to end up with. Okay. Before discussing this, notice that you can immediately ask, okay, how far can I push this? Okay, and there are at least a couple of observations that are useful to understand how far you can push it. The first one is you can replace that model with a linear model on what we call the feature map, but specifically a set of features. Okay, so this is phi jx, wj, and here we can run up to p. Okay. Yes. You can do that, okay? But it's a bit trickier. So whenever you talk about, and the main point is that whenever you talk about sparsity, sparsity is a concept conditioned to a choice of a dictionary, okay? What do I mean here? Let's call phi1, phi p, we call them features. In this world, they're often called a dictionary of features, or sometimes features are called atoms, okay? Atoms, whatever. And the idea is that you have a linear combination of these bases, not bases, they're just bases-like functions. Okay, they don't have to be linearly independent. They don't have to be a lot of nice things. They're just your set of. At this level, is the same of what we've been doing so far. Okay, but now notice that the norm we've been using. Assume for a minute that you have two dictionaries. Okay, you have this dictionary here, and then you have another dictionary, phi1. Phi p. Let's assume they're of the same size, and let's assume that they are, to make it super simple, let's assume they're linearly independent, and even better, they could be some kind of orthonormal basis, okay? This means that you can write the function f this way. Well, spoiler, I'm going to try to convince you, although it's quite obvious, that sparsity is sparsity with respect to a basis, and if you change the basis or the dictionary, you might not be sparse anymore. Okay, and this has not been an issue so far, but it is now. It has not been an issue so far because if you take, so this is the concatenation of the second set of features. So this is the feature map for this guy. This is the feature map for these guys. And what you have is that, the way we defined the norm so far was essentially the norm of the W's, but these that they're interchangeable set of features in the sense they're all linearly independent. You can also write this as like this, okay? In other words, the norm we were considering was somewhat invariant to some form of rotations of the features, okay? the features themselves don't matter. In some sense, it's the total energy they carry that matters, the L2 norm associated to them. So I can pick, if we do L2-like regularization, I can pick these features, I can pick their features, but there is a precise sense in which they're equivalent, okay? Particularly if they preserve the norm. What we want to introduce now is a different notion, and in some sense that it's not a specific sparse. You're not attached to that specific set of features, okay? In the way we formalize the notion of sparsity, now turns out that the features are important, and so we're gonna fix them, okay? They're gonna be fixed, and this should be clear in a minute. And so, because we assume that phi are fixed and we don't change them, we keep this notation, just because it's simple. So whatever we say for here, you can just replace it here. But the whole point is that it's fixed. It's not just any feature map. It's the feature map for which the model is simple. The way you... If you wish, the spoiler is that the way you define your sparsity is essentially by counting the number of non-zero coefficients in your vector, okay? So you take a vector. That equation basically says, go in a vector, read each entry. If it's different from 0, count 1. If it's equal to 0, you count 0, okay? Clearly, it's easy to imagine. Imagine that you just have, you're in 2 dimensions. You have a vector that points in the first direction. Now it's sparse in the sense that you have 1 coefficient here and 0 here. Now you rotate 45 degrees, all of a sudden you have 2 coefficients different from 0, okay? And you can keep on going in higher dimension. It's clear that you can even do just a small adjustment and have something which is sparse on a basis or on a set of features and becomes absolutely non-sparse once you change the set of features, okay? So this distinction is really important here because, of course, finding good features is important always, but here it's even more important because if you find the wrong one, you can go from totally sparse to totally non-sparse, okay? As we've been doing so far, we keep on cheating, and we don't ask how do you find that good set of features. We just assume that you do have that good set of features, that your model is sparse on those features, and you ask, okay, what do you do with it? Okay? So we are sticking to linear models, because as I said, from this moment on, you can imagine that we pick a basis, okay? We pick a set of features, and that's it. And what we have to do is that we want to, based on data, we want to find the coefficients, okay? But then it means that we are back to essentially solving a linear system. So not exactly new. And particularly, we put an emphasis on the case where, because we want to try to achieve sparsity, we try to look at a very big redundant dictionary of features, okay? So we're going to assume from now on that we're in the setting where P, the number of features, or if you want D, the number of dimensions, is much larger than the number of data. Again, the intuition why this is a reasonable scenario, because we're trying to achieve sparsity. So you want to have enough redundancy to capture everything is contained in your data and to have a lot of things that don't matter instead. So in this case, the picture you can draw is one where this matrix is short and wide, okay? The vector of unknowns is tall and thin, and we just have much fewer measurements, okay, much fewer data. So this is a case where we have many more, what you would call over-parameterized or undetermined system. You have many more unknowns than equations, okay? And again, there is no news up to now, right? We have been looking at this problem quite a bit. And so what did we do? We considered things like this. But we have already seen, and we're going to reiterate on this fact again today. In general, you cannot really expect that solution to be sparse. Okay, you cannot hope. You cannot. There is no reason to expect that the W that comes out of that is going to have 0 entries. In fact, we have already discussed quite a bunch of times that if anything, it's going to try to discard entries that correspond to certain small eigenvalues. So there is some kind of sparsity property, but not on the basis that we chose, which is in this case is just the basis, the canonical basis that gives me the entries of the vector. Okay. So the question is, This is fine, and we've been doing it so far, but it hinges, the very first class, somebody asked me, why this norm? Just because. But now, we really don't want to do it. So what if this is what we have in mind, that the vector has few coefficients, what do we want to do now? Okay? Still in pictures, if you want, the idea here is, if I have to solve this problem and I don't make any assumption, there is no way I can recover the right solution. Okay? But suppose now that I'm telling you that the true solution, there exists a true solution that you have to find. Okay? So it becomes the true one. Okay? That depends only on 3 entries. Okay? Well, then clearly you start to feel like we might have more hope to find it. Okay? Particularly, the problem becomes totally trivial if I tell you where they are. Okay? If I tell you not only that there are just 3, but I tell you that there are the 6th, the 11th, and the 12th entry of the vector, then what you do is that you just synthesize a new problem where you go and pick the 6th, 11th, and 12th column of this matrix, you build the smaller problem, you solve it, and now the problem become underparametrized. You overdetermine. You have many more equations than unknowns. Boom, you find it. Okay? The problem now is that you don't know where they are. Okay? So what do? You have to somewhat try to come up to a way to find them. Okay? Now, best subset selection which is kind of self-explanatory, is one idealized approach to do it, okay? And the way we're going to do this game is that first we're going to assume that we have access to an infinite computer, and you're just going to see what would be a way to do it, and then we're going to face reality and try to come up with approximate approaches, okay? So suppose that you have this handy infinite computer offered by Tommy and CBMM, and you have to find the best possible solution. What do you do?
Check basically subset of the columns.
Right, give me an order so I can then develop the idea. He's saying check all the possible subsets of columns. Let's just decide an order, okay? You can do it 1, 2, you can do everybody and less, or you can do it at random, okay? The first and the second are somewhat equivalent for our discussion. The third one is complicated, so we're going to pick the first, okay? So what do? Let's say a bit more slowly. You pick a column and solve the problem. The next column and solve the problem. You take each individual columns and solve the problem. For each one, you get the solution, okay? What do you do next? You take 2 columns. How? The first 2, the first and the third, all of them, all the possible, subsets of columns, okay? And then once you're done with that, you go to triplets, and then you keep on going, okay? Where is the regularization here would be essentially to find the smallest set that give you good, not only training, but also expected error, okay? So that's the idea. So the size, the number of columns become your measure of complexity. It should be clear from this description that that's why we need an infinite computer, because if this is 10, okay, columns, maybe, but if you start to become a bit bigger, depends how big is your computer, but it's gonna run out of juice pretty quickly, okay? And there is some small book from a bunch of years ago where this was called the torturing the data until they confess strategy, okay? Which I always like to share. And you kind of feel like you're torturing probably yourself as well as the data, but all right, so we're not going to prove it, but it turns out that what we just described, this best subset selection, is actually equivalent to consider this kind of pseudo-inverse or minimal norm solution. And it takes a little bit of work to prove it, but intuitively it should be clear. This is basically saying find all possible solution and find the one with minimal norm, which is the least number of columns that are allowed to predict the data exactly. And in this case, we are doing the same as we did before. We are not assuming you have noise and so on, okay? But that's the big difference. The big conceptual difference that we want to do from the 2 norm, which I have no reason to believe they're going to give me sparsity, to a norm which by definition is going to try to find exactly this coefficient generated by that basis that are going to be corresponding, not generated by that basis, that are going to be exactly 0. Okay? So this is the new minimal norm solution. And what we just described is a not super efficient algorithm to solve this problem. Okay? So if you want, from the modeling perspective, you're in a good shape, because we found a good way to define the problem, a good prior, okay? In the sense, a good assumption, small zero norm, and a good way to use the data, which is the same as before, okay? So the story here, if you want, goes develop in two directions. One is, what if I don't have what if I don't want to enforce exact constraint? What if I have instability, and so on and so forth? And there, that's where somewhat what we did is going to generalize nicely. For example, we say, don't do this, do some kind of penalization, okay? Or do some kind of constraint, relax this problem somehow. That's not the main point of this story. The main point of this story is at least to start to grasp how you can get something which is maybe not the fastest, but at least is efficient enough as opposed to not possible, okay? So how do we go from a combinatorial complexity to something that is manageable? And in fact, it turned out that we can do something which is relatively efficient, okay? So I guess this one is best subset selection, okay? So this is the min L0 norm, okay? And the related problem of best subset selection. And then the main idea is we need approximations. We give up solving that problem as hard as it can be in general, and we're going to look at two main approaches. The first one is what is sometimes referred to as greedy method, and the second one is convex relaxations. Okay? We do both because they pretty much, when you go and try to analyze their properties, okay, they have very similar property in the sense that they, up to some difference, of higher order, they tend to have the same kind of approximation guarantees, okay? And the first one is much easier than the second one, okay? It's just a very simple algorithm, while the second one requires a little bit more work, both to compute a solution and to understand why it's sparse, okay? So we try to spend not too much time on this and then to move on to this, which is a bit more interesting in terms of learning stuff. All right, so greedy typically refers to a procedure that somewhat try to incrementally find a solution which is better and better, and without solving the problem, face to face from the beginning. Okay, so the question for you is, I guess if you have not seen this stuff already, otherwise it's a bit boring, is I take away the infinite computer, but you still like the kind of idea that we described. How do you hack it in order to be able to implement it on your laptop? So the criterion we describe is all single columns, all pairs, all triplets, and so on. Now the question to you is, how do you actually change this procedure a little bit so that that it can be done?
If it's easy, then I'm suspecting that you find the best one column solution, fix that, find the best two given the first one.
Right. So that's the basic idea, is that you hear what he just said. Instead of looking at, the very first step is the same. You pick the best one. From that moment on, you don't look at all pairs, but you look at all pairs where the first guy you already chosen. And then you find the pair we just tried, what happens adding one. Okay? Clearly this now has a linear complexity in the number of columns. When you go for 2 to 3, you fix the first two, and you start whatever all the triplets where you fix the first two and you add one. And so, of course, the complexity is gone. Okay? This basic idea is called forward. Oh man, stage-wise regression. Or that's the name we're going to use. That's kind of the statistics name. It's an idea which, you can imagine, is not exactly a new idea. It's so simple that you can find it in the books. And another name is orthogonal matching pursuit. okay? I'm going to sketch the form of the algorithm because it's so simple. Although it's one of those classical things, it's easier to say than to write it down because then the notation becomes a little heavier. The basic idea is that we're going to do we will have to initialize, okay? We're going to describe the vanilla OMP, okay, not the fancy one, the simplest one. So you have to initialize, then you have to select, then you have to compute solution, okay? And then you have to update. And then you repeat, okay? So at the beginning, what you initialize that you get I is a set of indices, okay? Which is going to be the set of active indices, the indices of the variables that I'm selecting up to that point, which is going to be empty at the beginning, okay? Then I take, this is going to be an iterative procedure, so I take a W which is 0. And then what I do is that I take the residual at step 0 to be the data, okay? Everything is obvious apart the residual maybe at this point. The idea is that what we're going to do is that we're going to find a piece of the solution, okay? And then see what's left. And then we're going to find the next best variable. We're going to try to the best variable to explain what's left. And what's left is the residual. Okay, so the first round, we're going to try to fit the y's. In the second round, we already find a bunch of columns that can fit a piece of the y's. Okay, and so we're going to try to define a residual and try to find the rest. So again, this is going to be an iteration. And what you do is that let me call, if x hat is the matrix, I want to call x at j a column of the matrix, okay? And I keep the norm of the column around, but what you should really do is normalize the column size. Because it's clear from the beginning, if you have features that are rescaled in a funny way, one is the order of 1,000,000, the other one is called by 0.06. This is going to create a scaling of the coefficients, okay, for some reason. You see what I'm saying? I'm just saying if that matrix over there, you want the column of this matrix to be normalized in order to be able to assure that if a coefficient is big, it's big relative to the same reference point. Whereas if this column has norm 1,000,000 and this column has norm 0.6, then this is going to create some kind of problem with scalings. Okay, so let's see if I can write it decently. So first, you take a column, you take a scalar vector, you take, let me just write the first iteration and then we generalize to the next. So you write down the residual, okay? And then this is a column. It has the same size of the vector. So if you want to find the column which is closer to the output, okay, which is the one that solved the problem best in the least square sense. You can also rewrite these in terms of correlations, okay, trying to find the smallest angle. But it's the same, so we just keep this. Okay? Vj, okay, is well, maybe I can call it Vj. Doesn't matter. Sorry. Vj is the one number that for each column provides the solution, okay? Then what do? This is the select step. You put it here, okay? This is the value, how well this column solved the problem. And so you want to find the column that solved the problem best with smallest error, okay? And then let's call this J star. In fact, we can call it Ji, doesn't really matter. Okay? Is that clear? If I did make mistakes? So this is the first round. Pick the column and that have the smallest least square error. The computation are clearly super simple, okay? You just an inner product. This is is the select step, okay? But if you want, inside of it, there is also the compute the solution step, in the sense that I computed the coefficient to the new solution. What do I do now is that I take I0, and I now take the union with J star. So this is the update for the index set, okay? Then I have to say what is W, and this is the somewhat one way to say it, which is easier to say than to do. So what this means, you have a vector of all zeros. You take now the vector that has all zeros, but in the J star position. This is the canonical basis in the element J star. So it's exactly what I wrote here, all zeros but the J star position. And then I multiply by the one number I found so far, which is this Vj star, okay? Is the Vj corresponding to the J star element. And so I put it here. And then I sum them up. In words, you take a vector that has 0 entries, and one step at a time, you start to populate these entries with the coefficients that you found for that specific solution. Okay?
For the next step, you won't resolve the problem for the two columns from scratch. You assume that you have J star and you find the next J.
Right. So this is the first step. Okay. The second step. So this would be, say, E1. Okay. This will be W1. Then what do? You define the residual to be y minus, okay? This is how you define the residual. You found what you get at that point, okay, and you subtract it, okay? What do you do now is that you go from here, and the only difference is now you do this, okay? So you now try not to find the best columns that fit the vector, but just the one that fit the residual. This step is exactly the same, okay? Exactly the same, no difference. And now you just have to update the indices, okay? This is going to become W1. This is going to become W2, 1, 2, and this remains the same. Yep. We're going to do it in a minute, okay? So I think, just to, I always forget to repeat comments. So the first comment is, if I understand correctly, is, pointing the finger to the one point where you break the combinatorial complexity. This is it. Because you see from now that I never look at the problem with two columns in an exhaustive way. I just add one column at a time, okay? And the very important bit is this one, okay? The one where you select. And you only select only one column. That's the important bit, okay? So this is the one that you don't want to touch. If you start to touch this, it's going to be tricky, okay? If you understand the second comment is more about this way to update the solution, okay? And that kind of leads to an improvement of this algorithm. Let's discuss 1 second, see to be sure that I don't make mistakes and you understand. Yes?
How do we make sure that, for example, the second J star is not going to be the first one?
Well, in general, you can. At the point you get stuck, you might refine the indices a bit and you don't expect. This is a greedy algorithm, right? So, it will only, if you think what it will happen in very special a situation where, for example, the vector is essentially in the same direction as that column you pick. Otherwise, it's going to change at some point. Other questions or comments?
Was you saying that the argument is taken over, it's like the numbers 1 to n and then set minus?
No, you keep on going. Yeah. Because because what might happen is that, so the question that everybody's asking is, are you taking off the one that you selected, okay? And the answer is no, because what you expect is that, for example, what might happen in this case is you pick, make it simple, you pick the first column, okay? You compute an index. Then you pick the second column, and it turns out that, for some cases, that's the second most important one. The moment you compute the first column, you didn't know that you're going to have at disposal a second column. So now that you have both, maybe this is going to change a bit the way you want to put coefficient in the first column, okay? Because now the residual is going to change. So the fact that you picked it again, it doesn't mean that you're going to get the same Vj star. So it might be that you go in and you correct a bit, okay? There's no reason to believe one way or another, but in general, this can be the case, okay? Do you see what I'm saying? Each time if you keep the same variable in the batch, each time you look at them, you are comparing them to a different residual, and you compute a different coefficients. So there is no reason to believe that this is not going to be a useful thing to do, okay? Because every time you selected it on the basis of what you knew before, but not what was coming afterwards. You know, the other kind of column you would get that would change the residual. Yes? No, I think that twice in a row you don't get, because you get the, I think twice in a row you don't get it, but I think it might happen you get it, after one or more. Okay. Yep.
So after you choose a column, never look at it again.
Say it again.
After you choose a column, never look at that column again.
No, that's exactly the opposite of what I was trying to say. When you pick a column, you can look at it again when you pick future columns. So again, you pick this, the next one over you pick this, then you might pick this one again, then you pick another one, then you might pick this one again, because every time you correct the coefficient, okay? And it's conceivable because, again, if it was always the same vector, but if the vector changes, this might happen, okay? That's the bit that changes in the procedure. The residual changes at every step, okay? Yep. That's the cross-validation moment of the class. Right, the question is, how do you choose the number of iterations? And if you wish, call it lambda, okay? It's just it. As in every class we do, there is one point when one recognizes there is something that you might have to choose carefully. You might have to just choose as small as possible, but you might have to choose carefully, do some kind of validation test, or your favorite marginalized likelihood, whatever, okay? Stein is sure estimator. But that's the one point where you just have to say who's lambda, okay? And lambda here is the number of iteration, and it's more like 1 over lambda, okay? T larger, you have more complex model. T small, well, I guess I shouldn't call this n, I should call it t. The more complicated is the model, okay? And here, if your goal is really not prediction, but finding the most important variables, cross-validation might suck even more, okay? Because in some sense, the criterion is just looking at prediction error is not really obvious at all. This is one thing you want to do when you look at whose variable has an important coefficients. And this created a certain amount of extra statistical tests and criterion to try to do model selection in a more efficient way, okay? There was an explosion of work on all this stuff for the, between 2000 and 2015, and still now. Yep.
How does it ensure sparsity? Because as we keep iterating, like more and more columns will sort of become non-zero.
Yeah.
And there's no reason to believe that the solution where you just get a good answer with it.
No. Yeah, so if you understand what he's saying is, you begin with a 0, then you start to populate it,
Yeah.
and it might be that at some point it doesn't become sparse anymore.
Yeah.
Fair enough, it just means that your assumption was wrong.
So when you move towards a good solution, like an approximate solution, and you're also losing sparsity simultaneously.
Yeah, but that's kind of the rule of the game, right? You say, I assume my model is sparse, and I try to make it as sparse as possible. Then I try to make it less sparse and see how well, and then I try to find the best possible sparsity. You're like enforcing this norm, right? This is a way to explore this norm. If it becomes totally non-sparse, it just means that your idea that a good solution could be sparse is wrong. And maybe you should, maybe it was because, well, maybe it's just because you don't have enough data to uncover that sparsity, okay? Or maybe just because you choose the wrong features and the model is really not sparse, okay? The main point of this is that it's not that you're ensured to get a sparse solution, but at every step you have a sparse solution, okay? So if you can stop at some point, you do get a sparse solution because you have a bunch of zeros by construction. You don't have to threshold anything. You literally just populate the thing which is full of zeros with non-zero numbers. Yep.
Why do we not just every time we add a new column, update what we did?
No, that's what's he just said, and it's the next slide. Okay. So the question, the tempting thing would be to not do this. Okay. You do everything. Okay. You do compute the best possible column. You add it to the set, and then what do you do? There are a bunch of different ways to write it, but let me write it like this, okay? Again, it's more complicated to write than to explain. What do you do is that you know that this indices in the active set. You can now create the vector, which is a full vector with a bunch of zeros in the non-active set, okay? And then you solve the new problem. In words, which is easier, every time you select a column, don't just update the solution you already found, but recompute the solution with the column in the active set. Okay? Because intuitively and provably, this is a better idea. This, if you wish, was the orthogonal part that I already put, but is actually, this is it. Okay? What we just explained up to here is called matching pursuit. And the story that you recompute every time you select with the column in the active set is the orthogonal matching pursuit. And you can show, and we're not going to do it, that the name stems from a reasonable geometric observation. Okay? Of course, in the second case, you compute more. In the first case, you only have to solve just problem in one dimension. In the second case, you solve sub-problems in higher dimensions. So if, you know, as you were saying, if you have bad luck and your problem is not sparse, at some point you're going to be solving essentially the square problem, which is as large as the number of rows. Yep.
So picking the next column is still based on
Yes.
one dimension.
Yeah. So what he's saying, the observation is, the selection step remains the same, and the answer is yes, and that's crucial because if you mess around with that, at some point you go really towards hard problems. Yes?
So, like, say that there is a sparse solution. Does this algorithm have any guarantees on it? Like, it finds a solution that sparsity is like within a constant factor or something about it?
Right. So just repeating the question, we start from a point that we say it's hard. We introduce the solution. Will it ever work? Okay. And if it, in which sense do we know it works? And people just got super excited about all this because indeed they could characterize classes of problems for which it works. Exactly. So they basically gave condition over x and w. So assume that so the basic result, which you know, I would have explained a bit more, but maybe this is a good point, is assume that you have no noise in the out. So it's not a learning result. It's just a pure linear algebra result, okay? So you have a matrix, and then you can develop more refined results. But the basic result is you have this linear system. You know that it exists a solution which is sparse. Tell me condition on the level of sparsity, n, d, and x, so that this is going to recover the exact solution, okay? So it's exactly what you wanted. There is w star. It has S entries that are non-zero. You have a matrix with n row and d columns. Can you find this solving, say, first this problem? Okay? The answer is yes. The second question is, and that's for all. And the second question is, can you solve it using this problem? Okay? And roughly speaking, the result there says that if there is a geometric result and a probabilistic result. Let me tell you the probabilistic result because it's a bit easier to state. Assume that your matrix X has Gaussian entries. Okay, so it's a random matrix. And the reason why this is important is because in some sense this ensures that the probability of having very collinear columns is unlikely. Okay? In theory this is important because even if you knew, imagine that if you knew these 3 points, these 3 entries, still if the corresponding columns are very collinear, it might be hard to find them, right? Because you cannot invert the linear system. But if they're quite far away, it's a good idea. So the one basic result basically says, assume that this is a matrix with Gaussian entries, okay? Then if, and I give you the simplest result because it's the one that carry the basic idea. If the number of rows is larger than sparsity times the logarithm of the dimension, then you're in good shape. You can improve this result in a bunch of different ways. There are constants, there are stuff. But this is the one that maybe it's good to remember. And that makes sense, okay? Perhaps the one that would really make sense as you see it. Well, this makes sense, okay? Why? Because suppose that I tell you where the entries are. That makes sense? So this is the condition. So suppose that I tell you where the entries are. Then the rule of thumb is as many equations as unknowns. The unknowns are S. The equations are N. So if N is order S, you should be able to do it, okay? And then in some sense you ask, okay, what is the price I pay for not knowing where they are? And if you wish, this is the price you pay. And of course, because you're scanning all dimensions to find the right ones, this has to be dependent to the dimension. But as you see, it's a very weak dependence, okay? So for these kind of problems, which is just a subset of all the possible problems, all possible problems you cannot solve. But for this subset of problems, where the sensing this input matrix is super nice, and you have these many rows compared to the sparsity in the columns, then you can, well, I guess, then this works, okay? And you can make the statement precise, okay? And there are, at this point, there are a few books about this, okay? There are a few books on the statistical side, okay? And there are a few books where the high-dimensional statistics point of view was really pushed hard, okay? And then there are a few books more on the sampling theory side, okay? Because maybe I don't have time, I won't discuss it, but there is a connection here with the Shannon sampling theorem. Shannon sampling theorem, for those who remember, basically said that if you want to sample a signal, if you want to construct a signal, you need to sample at twice the maximum frequency. And that's correct in the worst case, where every single frequency in the band is present, okay? So the maximum frequency is some W max frequency, and then every frequency up below that is present. But assume that I tell you that I have the maximum frequency and just other two frequencies, okay? Can you do better than that? It's not unreasonable. And it turns out that the answer is yes. You get somewhat an effective Shannon sampling that says, if, in some sense, the maximum frequency becomes the dimension, and the number of frequencies that are non-zero in the band becomes S, and then N becomes the number of sampling points a la Shannon, okay? So this connection can be made precise. And so you find the literature of this in statistics, in compressed sensing, in signal processing equally like, and in compressed sensing is the name, compressive sensing or compressive sensing is the name it has in the signal processing literature, okay? Where of course the setup are slightly different, and one end with the emphasis on deterministic objects and worst case object, the other one you really take all advantage of, you know, the fact that you might have zero mean quantity and things like this. Okay? So where do we stand? We did a bunch of things, right? We changed assumptions. We said not minimal norm, but minimal L0 norm. Why? Because it's related to sparsity. We said the corresponding computations are unfeasible because they explode combinatorially. And we introduced the first algorithm that is obviously elementary and not combinatorial anymore. And in fact, we introduced two different flavors, the basic matching pursuit and the orthogonal matching pursuit version, where you recompute the solution with the columns directive set up to that point. Motivated by the question, we also commented briefly on when would we expect this thing to work. And again, the two things which I think are worth remembering is, even if I knew where the entries were, I need a way to ensure that the matrix on that entries is invertible. Otherwise, good luck finding them. And two, if you don't know, you have to know how much you pay. Okay? So in some sense, these are the two main ingredients to be sure that this algorithm can actually work. Okay? The second approach, which perhaps is even more popular, is L1 regularization. So the basic idea, and again, we're going to follow very much the discussion above, is that rather than L0, we're going to look at this. Okay? In words, each entry of a vector doesn't count 0 or 1, but count how big it is, okay, in absolute value. Clearly, why the indicator function on each entry is a non-convex function, okay? This one is non-differentiable. It has a kink, it's an absolute value, okay? But it is convex, okay? So this is why you might call this a convex relaxation. The associated problem is this one here, okay? And this is a bunch of names. I think the two names that are floating around this idea are usually basis pursuit or basis pursuit denoising in some other version. Lasso or lasso, or I don't know. It's the more statistical name. This is more signal processing. It turns out that many of these ideas were somewhat studied and pushed in parallel in statistics and signal processing. And this is what you call the L1 norm, okay? Now, notice that now the distance between this and what we've been doing for a month is a 2, okay? That's the main difference, okay? So a question you could ask is, what does this difference make a difference, okay? Does it make a difference or not, okay? Is it really important or not? And we're going to see this in a couple of different ways. One, we're going to just look at the geometry, if you want. These are the two standards way, okay? One is to look at the geometry of this problem, okay? And just realize what this means. And I'm going to ask you a bit of imagination, because to make the drawing, I need you to imagine a situation where we have 1 point and 2 dimensions, okay? Because that's the only way of drawing it. So the idea is that, say, this is the dimension W1 and this is dimension W2, and we kind of have to imagine what the picture would look like, okay? And then we want to draw what does it mean to find the solution to that problem, and convince yourself that indeed it could be sparse and it could be the same as the L0 norm. So what we want to draw are the set of W that satisfy this equation, and then the shape of this ball. And then among all the W that satisfy this equation, find the smallest ball that is going to intersect the set of points, okay? It's like the graphical kind of solution to this problem. So if you had to draw this, what would you draw? Again, if you had to draw the W in 2 dimensions that satisfy this equation, that's where I need your imagination a little bit. A point, a line, 2 points, 5 lines. It's a linear equation, and to make this whole story meaningful, we are assuming that it has multiple solutions, okay? And so what it's going to look like is a line. There are many solutions, and they all satisfy a linear equation, okay? So something like this, okay? And again, that's where you need a bit of stretch, because to actually do it, it means that you have 1 point and 2 variables, okay? So this is just more of a toy illustration. Is that okay? What about the L1 norm? Because what we're going to do is we're going to draw it, and then we're going to ask, where do they meet? Okay? And my drawings are really so bad that I don't even know if I understand it. So it's easy to convince yourself that that's the shape of a L1 ball, okay? Draw it. It's just an absolute value of this, an absolute value of that in 2 dimensions. You have to just take what they're doing in all the 4 quadrants, and that's the shape it has. What does it mean to find the W that satisfies at the same time the constraint and is minimal in the ball? Inflate the diamond, which is now your L1 ball, until a point on the edges of the ball touch the line. Where this is going to happen, hopefully you see that it's going to happen here, okay? And this is not an accident. It's going to happen basically all the time unless your line is perfectly close to be 45 degrees, okay? So this suggests that the geometry of L1 is such that you really find a sparse solution, because if this is the point, it means that the second entry different from 0, but the first entry is exactly 0. Make sense? So if you've seen this stuff before, I ask for your patience. If you've never seen before, you have to wrap your mind around the picture But that's kind of a standard way to somewhat describe the geometry of the problem. And maybe if you go in more dimension where you really have a, a cubic-like thing and then a plane, and you start to see that geometry is a bit more interesting. You have edges, you have planes, they can touch each other in multiple ways. And of course, proving this is another business, okay? And induce high-dimensional statistics and high-dimensional geometry because you have to be sure what's going on. Is that okay? While you digest this, we can now think a bit does it mean to do L0 and L2, okay? The easy one is L2. L2 would be, if you put the square, this would be a ball, just a ball. If you now inflate the ball, the round ball, what's going to happen? You're going to touch line where? Somewhere. But quite likely not in one of the coordinate axes. So it's kind of the reverse situation as before. This can be sparse, but it means that your line is either vertical or horizontal. Otherwise, it can be small, but not. We already used this idea that doing ridge regression was shrinking, so there is some meaning in that. But we see now that it's not doing any kind of hard thresholding on the coefficients, okay? Whereas if you do L1, intuitively it does. That's where you inflate when you make the L1 ball round by taking here a power which is higher. Anything between 1 and 2 would be somewhat in between, and we're going to comment in a minute. If you go 0, and these are all convex shapes, if you take the norm here, where is it? Here, to be smaller than 1, okay? So if you take now a Q norm, which is Q1 over Q, when Q is smaller than 1, then you start to get a concave shape, okay? Something like this. And if you push Q to 0, then you basically got the cross, okay? So that's clearly something that is always going to be sparse. But this suggests that L1 is the first convex relaxation that essentially preserves the same kind of result. And you'll see again why the fact that you need some kind of geometry of the columns is important. If they start to be very close to be indistinguishable, then you lose this identification property that you can recover the right directions. Okay? So again, L1, L0 is going to be essentially the limit case of these deflated balls, okay? L2 is the round ball, and L1 is this. And in this sense, L1 is the first shape which is convex and still kinky with a kink, which is enough to get the right solution. Okay, that's one intuition. Again, proving this is a different business, but drawing it hopefully makes sense enough. Okay, so this is the first reasoning why moving from L0 to L1, again, it might not be the same, but there are conditions under which they're the same. And it turns out that the conditions are not too dissimilar to the condition for which metric pursuit does work. Okay? Yeah, so the question is if this is the case where it fails. The answer is essentially yes, but also remember this is a one-dimensional drawing. So it's in more than, when D is much bigger, then you will have, rather than just have a face and a line, you can have a plane, and then you're going to have edges, corner, faces. So it's a bit more complicated than that when you go in higher dimension. But roughly speaking, you can find an analogous situation. Does that make sense? You do have to imagine high-dimensional stuff.
I'm wondering, how is my low-dimensional imagination failing?
It's a bit complicated. I would say roughly, you're going to have this kind of condition are for any dimension, as you see from that. So that's roughly, that's still, again, you can improve that, but that's roughly the idea. Okay.
If he doesn't interpolate the data, before we add this square loss of xw minus y to the Olympian one this time,
Mm-hmm.
then again, do we get a sparse solution?
That's what we want to do next. So the question is, I'll do it here. The question is, if you now move from the mean norm solution, the pseudo solution, or whatever you want to call it, to the actual, penalized risk, empirical risk. Okay. So if you now consider this, and maybe I'm going to skip this for sake of simplicity. Okay, is the solution to this problem still sparse? Okay, and we can go after this question in two ways. One is to draw the picture, but I gave up on pictures. So we can actually go another way, because we take two pictures with Watsons and ask, how do you compute this solution? And when we compute this solution, we're going to see that in the way we compute it, we actually make it sparse. So the answer is going to be yes. Okay. Of course, when you move on to this, you do it because you think that somehow you have to be robust towards something. Like that was the same story we did for least squares. We moved from the mean norm solution to something like this because there was some notion of noise or perturbation and we want to be too robust to it. Okay. So we're going to discuss the computation only of this, though. In the case of least squares, we discussed everything. Here is just the computation of this. And again, in the process, we're going to discover that the way we compute the solution is going to give sparse solutions. Now, the question here is, how do you solve this problem? How nice it is, or how not nice it is. The first term is super nice, is smooth, in the sense that it's differentiable, is convex, okay, although not strongly convex. Then we have this. What about this? Is this convex? Is it differentiable? Have you learned in an amazing course in the last month an iterative procedure based on the notion of left derivative? So the thing you could do is to say, I'm going to consider the subgradient method. Okay, the subgradient of this is going to be the differential. The subgradient of this is very easy to find, okay, because it's just absolute value. And then you play the same trick as you did before, okay? And that's one way to go, but it turns out that the algorithm will generally not give a sparse solution and will be pretty slow. And it turns out that another big trend in the last quite a few years has been realizing that for problems with this very specific form, and for L1-like stuff, there is another way to go, okay? And these are essentially what are called proximal or forward-backward splitting or just splitting methods. Okay, these are actually two sets of ideas, but they often are conflated when you describe this method. Okay, and here's the basic. This is the basic thing. Suppose what is the structure that you have here? You can abstract it by basically saying that you have one function, so that your objective f is actually the sum of two functions. I give this name because we're going to think of this as an error and this is regularization, but this is general. And the thing is that this one is just convex. We're going to assume that they're always continuous, albeit you can do something more than that to deal with constraints. But assume that this is convex and this is convex differentiable. Okay? That's the assumption we make, which is true for us, right? Then it turns out that we can now split. We can now write down an algorithm which is iterative. It looks very much like a projected gradient, okay? It's going to compute the gradient and update the solution iterative every step, and then compute a projection-like operation, which is not quite a projection, and it's called the proximity operator or proximal operator. So who's differentiable? This guy, and that's going to contribute a gradient, okay? So suppose that we had no R, then we would get a W. So let me write the same way I did it here. Wt minus gamma okay. If we just had E, that's what we would do, and how we would choose gamma. Convex, differentiable, okay? Then I might be able to write a constant step size and be sure that it does converge, depending on the Hessian, right? If you have a bounded Hessian, then you can pick that to be a constant. For subgradient, you cannot. It's not a decay, it's not a descent method, and you have to take a decaying step size. For a stochastic gradient, you cannot. But for vanilla gradient descent, that's exactly the case where you can do it, right? Unfortunately, that's not our problem yet. We forgot about R. Now, it turns out that for R, you need to apply something. This prox is a nonlinear map and is defined as follows. The prox R of W is equal to okay, let's read it, okay? Let's read it a bit to digest what it means and why it's a bit funny. So this nonlinear map is not just a projection, it's something that looks a bit more complicated. It looks itself as the solution of an optimization problem, okay? The optimization problem, at least in our case, looks very similar, because if you look, our E is just this guy. The main difference is that here there is no X. You take the identity. It turns out that this actually makes a lot of difference, okay? But clearly, this whole story makes sense if the computation of this second problem is easier than the computation of the minimum of F itself. Otherwise, it's a bad idea, okay? So the questions are two. First of all, assume that you can compute this and forget about the costs. Will this converge to the solution to the problem? And second, are there good examples where you can compute this? Okay? These are the two questions.
So you have another optimization problem that also has non-differentiable
Mm-hmm.
part, but it's easier.
That's a hope, right? Otherwise, this whole story doesn't make sense. But even before you ask that question, you can ask, assume that it is. Will this converge? And how do I have to choose the step size? It's not clear, because this is not a gradient method. And we already know that we could do the subgradient, so it's worth going and sweat if it does work. And long story short, the answer is yes, okay? This algorithm for the constant step size, in some sense, it smells like gradient descent, okay? Because you can pick this constant step size and you can pick the constant step size the same way you would do if R was not there. There is a complete split, okay? The E part contributes a gradient and the choice of the step size. The R part contributes this proximity operator, okay? The convergence rates are the same as gradient descent, not subgradient descent, okay? And the proof is essentially the same up to some abstraction. So in some sense, this algorithm is very much like gradient descent, okay? In our case, it becomes particularly simple because this is just the gradient of the, this part is easy, right? It just becomes the gradient of the least squares. And the question is, can we compute the proximity operator in a nice way? And the good news is that in the P set that we gave you today, you're going to do it 3 times. Just to be sure that you convince yourself that is, yes, you can do it. But let me give you the spoiler. The proximity operator, the forward-backward splitting approach for that problem is often called ISTA, which stands for Iterative Soft Thresholding. And the name stems from the following observation. WT, so I'm just gonna rewrite this in our case. And I'm going to tell you how this gradient look like, which is trivial, but also how this looks like. So say prox of lambda. Where do I have it? Okay, so that's the easy part. We have the gradient of the least squares in the middle. We have the constant step size as promised. The way you choose the step size, wow, this is really loud. The way you choose the step size is the same as gradient descent. The question is, what is this? Okay, and I'm going to write it down. And we can, the nice thing is that this decouples. You can just explain what happened for each component separately. So this is a map that takes a vector and returns a vector and depends on the kind of regularization we consider. Here is the L1 norm. But we can describe what happens to every coefficient separately, okay? And what happened to every coefficient is, so I have to tell you what happens to Wj. And what happened is that if Wj is bigger than gamma lambda, well, let's say that what is the important bit. If Wj is within minus gamma lambda and gamma lambda, I set it equal to 0. Again, in words, I go in and check the entry. If it's small, in the sense that it's between minus gamma lambda and gamma lambda, I kill it. Okay, so at every step of the gradient, I don't only do a projection, I do a soft thresholding operation, in the sense that well, in this case, this is a thresholding operation, okay? I go in, if it's small, I take it out. Why it's called a soft thresholding? Because when it's big, I don't just let it be, as I should. What I do is that I deflate it a bit, or inflate it a bit. Okay? So if you run this algorithm, this is if you want to answer all the questions, okay? Does it converge if you can compute the proximity operator? Yes, because there is a result that essentially shows that this algorithm is closer to gradient descent than it is to subgradient descent. You're picking a constant step size, and it will converge with the same rates, okay? And we don't prove it, but you find it in a bunch of references, but also in the appendices of the notes. Here we ask the second question, which is, can we, because we did this strange cheating that we replaced the problem with another problem, can we solve it? And this is the solution, if you wish. The solution to this problem, when you put this here L1, is a simple soft thresholding. Pick a vector, look at the entry. If they're small, swap them out to 0. If they're big, decrease them a bit. If they're small, increase them a bit. Okay? If you plot this curve, if you put W, it's going to look like this. Okay? This is W. This is also called the proximity, the soft thresholding operator. This is gamma lambda. This is minus gamma lambda. Okay? So around 0, ship it, and big and small enough, you just don't let it be. You know, if you didn't do the soft thresholding, it would look like this. Instead, you move it up and down a bit, okay? And this creates a little bit of a bias, but makes the problem a bit nicer from a computational perspective, okay? All right, so let me wrap up. The only point I want to make is L1 offers another perspective. The same kind of guarantees that we discussed would work, you know, under this kind of thing would work also in this case. You can compute things, and essentially it's because the proximity operator is nice. It turns out that this idea generalizes in a bunch of ways. Whenever you have sum of norms, sum of absolute value, like regularization terms, you can solve them that way and use proximity-like operators. So things like structure sparsity, group sparsity, matrix sparsity, rank sparsity, whatever, okay? It's all, you know, once you have this, you only have to do so much to understand those other variations. It's more like in the way you compute this guy or in the way you do the picture, okay? Okay, I'm a bit late as usual, so I'll stop here. If you have questions, I'll take them offline.